So, continuing my sort of march towards B trees, today we're going to talk about 2-3 trees. We had binary search trees, and they're fine when things go well for you, which, you know, might be usually, but sometimes things go terribly wrong. So in this case, if I give you the values 5, then 1, then 3, then 10, 30, 100, 32, right on down the line here, you end up getting something that looks a lot more like a vine than a tree, right? It doesn't branch nicely. It's completely unbalanced. And basically, if you want to search for a number, let's say the number 98, it feels a lot more like a linked list than a binary search tree. I mean, I'm going through almost every value in my tree in order to get to that 98. So several different data structures have been developed, which basically figure out a way to keep the tree more balanced and more nicely branching. And all of those data structures, or most of those data structures, use something like a rotation. And what a rotation is, it sort of makes the observation that, hey, if I have something like this, what I could do is I could rotate my 10 up. I could rotate my 5 down. And if I did that, I would end up with a more balanced binary search tree. Okay? So I think the first data structure that sort of maybe was a balanced binary tree using this was maybe an AVL tree. The book goes over red-black trees. There are splay trees. There's a bunch of different data structures that do this. I'm not going to go over any data structure that explicitly asks you to make a rotation, but I will come back to rotations in a later video. I'm not gonna go over these because sort of the rules of the data structure tell you when to do rotations, and my memory is hideous, and I can't remember when to do rotations. I mean, so instead of doing that, I'm going to go over a sort of a balanced binary-ish tree structure where you don't actually have to remember explicitly when to do the rotations, even though there are rotations that are sort of implicitly happening. Okay? So in order to talk about this, I'm going to ask a question. The question is, why is a binary search tree binary? Natasha. Okay, so for those of you who couldn't hear, Natasha suggests, well, because they have 2 children, and she looked at me like I'm an idiot. Okay, so Ms. Romanoff's point is fine. They do have 2 children, but I'd say the reason they're called binary search trees is because they have up to 2 children. It's not that they have 2 children because they're called binary search tree. It's sort of a cause and effect difference there, right? They're called binary search trees because they can have up to 2 children. Why are we limited to 2 children? Bruce. Okay, well, that actually mentions my next slide. Bruce suggests that I can just make them not binary by adding another child with the sort of value equal to the key of a node. Yeah, that's kind of like 3 children, but not really. I mean, this middle child is not, it's not equal to the other children, right? So Mr. Banner's suggestion is no good. Hey, don't get mad. Anyway, so the idea here is, I mean, this left child covers this big range of values, everything up to 10, everything less than 10. And the right child is everything greater than 10. And this middle child, oh, it's exactly equal to, that doesn't seem fair, right? This isn't a valid third child. But when we start talking about ranges, we actually have the reason why binary search trees are binary. They're binary because each key cuts a number line into 2 parts. So this 10 cuts the infinite number line from negative infinity up to infinity into 2 parts, right? And this 30 cuts its number line into 2 parts. We go from 30 up to infinity. And 10 up to 30, right? And our 5 Our 5 right now it's in the number line that goes from 10 down to negative infinity. Well, 5 goes negative infinity up to 5, and 5 up to 10. And each node is sort of in the middle of some number range, and it cuts that range in half. That's why binary search trees are binary. Okay? If we want to make binary search trees not binary, we have to allow for actually more than one key. One key cuts a number line into 2 pieces, but let's say 2 keys cuts it into 3 pieces. If I say, look, I give you the numbers 5 and 10. That breaks our infinite number line into negative infinity up to 5, 5 to 10, and 10 up to infinity. So that's the idea that's going to be used behind 2-3 trees. Each non-leaf can have 2 or 3 children, and the way that we get that to happen is by saying each node can have up to 1 or 2 keys, right? Now, if a non-leaf has 2 children, it's because it has 1 key. And if a non-leaf has 3 children, it's because it has 2 keys, right? 2 keys. 2 keys breaks the number line into 3 parts. And this is going to allow us to have a nice balanced tree. So balanced that we can actually force every single leaf to be on the same level. And we do have a variance in the number of children, but instead of having nodes with sort of 1 child or 2 child, where 1 is really bad, it gave us this linked list, binary search vine. Instead, now we've got 2 or 3 children. Both of those are nice. They both have branches, either 2 branches or 3 branches, right? So now we're going to take this and we're going to say, well, let me build a tree like this. I say, well, I'm going to insert these numbers, 5, 10, 20, 8, 7, 15, 30, 11, into a 2-3 tree. And, well, okay, I insert a 5. There it is, my 2-3 tree. You're welcome. Okay, so now I want to insert a 10. Just like in a binary search tree, I'm going to start at the root. I start at the root. Hey, the root happens to be a leaf. Just like in a binary search tree, I'm going to go down until I get to a leaf, and I'm going to, try to insert at or in the leaf. I guess in a binary search tree, you always make a new leaf. In this case, I get down to a leaf, and I insert there. My root in this case was a leaf. I insert 10 into it, and I'm done, because I'm allowed to have up to 2 things in a node. Now I want to insert a 20. Go to my root of the tree, and what I'm going to do is I'm going to say, well, try to insert it. Oh, this doesn't fit. I'm only allowed to have 1 or 2 keys, right? So if I'm only allowed to have 1 or 2 keys, I say, well, let me temporarily imagine I have 3 keys. And now, how do I fix this? The 10 node can be split out of the other nodes, splitting them apart. This is splitting a node. Oh, the 10 comes out, the 5 becomes its left child, the 20 becomes its right child, and now I have a valid 2-3 tree again, okay? Now I want to insert an 8. I come to my root, 8 smaller than 10, go to my left subchild. The left subchild is a leaf. I stick it in that leaf, and there's room for it. I'm done. Now I want to insert a 7. 7's smaller than 10. Go to left subchild. It's a leaf. Try to insert a 7 in there. Now we say, hey, again, the leaf is now too full. It's over full. So I'm going to split it. Bring the 7 up. I'm going to take this 7 and split it, bring it up. And it's going to split the 5 and 8 apart. There you go. The 7 moved up to its parent, and the 5 and the 8 came apart. Now, when we split the 10 out, it had no parent. It became a new leaf of the tree. I split the 7 out. It just moves up into its parent node, right? Great. I want to insert a 15. Stick it into the, 15 is, probably I compare the 15 against the 7. It's bigger. I compare it against the 10. It's bigger. In this case, I actually needed 2 comparisons to get down to one of my children. I get down to a leaf node. Hey, stick it in the leaf node. That's fine. Now I want to stick in a 30. 30 is bigger than 7. It's bigger than 10. Come down to this child. It's bigger than 15. It's bigger than 20. I try to jam it into this leaf. This leaf is over full. I split up the middle value from that leaf. The 20 moves up. The 20 moves up to the parent. Oh, there you go. The 20 moved up to the parent. But in this case, the parent became over full. The parent now has 3 keys, and we're only allowed to have 2 keys. So again, the middle node from the parent moves up. So there we go. Hey, look at that. It's a very nicely balanced binary search tree in this case. It happens to be binary at this instance in time, but it doesn't need to be. And of course, if you insert an 11, hey, 11 is bigger than 10, it's smaller than 20, it's smaller than 15. I insert it in there, and there we go. There is my 2-3 tree for these values. Okay. Now, some quick analysis. Each non-leaf has 2 or 3 children. So the height of the tree is, well, it's sort of at most log base 2 of n if all the nodes are binary. And it's at least log base 3 of n if all the nodes have 3 children, if all the nodes are tertiary, right? So this gives us a logarithmic height. And every time you insert or search in this tree, we could do search in the same way that we did search in binary search tree, basically, except you might have to check 2 values at each node instead of 3. But every leaf's at the same value of the tree. The height of the tree is logarithmic. We get one difference is, well, the root seems to be moving up instead of the leaves moving down. Neither one of them seems to match an actual tree, but that's okay. We don't get outdoors much. In order to do insertion and search, it takes logarithmic time, right? It takes time proportional to the height of the tree. First, you do sort of a search that gets you down to a leaf, and then maybe in inserting, maybe a value sort of pushes up the height of the tree. But every level of the tree that you go through takes constant time, so this is a logarithmic runtime, okay? I'm not going to talk about deletion for these. We will talk about deletion when we finally get to B trees.